Hello, in this video we're going to talk about limiting reagents. Up to now we've been talking about stoichiometry, how the relative amounts of chemicals react with one another. We've been saying that we've got the exact amount to make the reactions occur, that we have a stoichiometric amount. But oftentimes we don't have the exact amounts. We have more of one reagent than the other, in which case you need to determine what's the limiting reagent. The limiting reagent, as its name says, limits the amount of product that can be formed in a chemical reaction. If one of the reagents is the limiting reagent, the other reagent will be the excess reagent. It's present in a quantity that is greater than necessary for the reaction to occur. So we're going to have the limiting reagent. They'll oftentimes refer to abbreviate as XLR, and sometimes I'll abbreviate the excess reagent with these letters XS for excess reagent. And so let's look at this problem. 18.4 grams of methane is combusted with 22.7 grams of oxygen. What is the theoretical yield of carbon dioxide? So we need a balanced chemical equation. It's a combustion reaction. So we're taking the hydrocarbon CH4, burning it with oxygen, and the products of combustion reaction are carbon dioxide and water. So we need a balanced chemical equation. We've got one carbon each side. Try 2 in front of the water. Now the hydrogens are balanced. We have 4 of those on each side. And we've got 4 oxygens on the product side. Let's try 2 in front of the O2 on the reactant side. And now we got the balanced chemical equation. So the stoichiometry is 1 mole methane plus 2 moles of oxygen makes 1 mole of carbon dioxide and 2 moles of water. So the way I like to do limiting reagent problems, in the way I think is simplest, is to work the problem twice. Once with each reagent. What we're going to do is calculate the theoretical yield for both of these. And then we're going to compare the theoretical yields. And then we're going to choose the one that gives us the lesser amount. And that will be the amount based on our limiting reagent. So in all of our problems, when we're doing stoichiometry, we'll be doing grams to moles to moles to grams, using the molar mass to convert to grams to moles or moles to grams. and using our stoichiometric ratio to go from moles to moles. So let's take our 18.4 grams of methane, convert moles methane to grams methane. It's 16.0 grams per mole. So grams methane cancels. That gives us moles methane that we want to convert to moles carbon dioxide. Our stoichiometry just happens to be 1:1, but we want to include that step anyway. So that moles methane cancels, we got moles carbon dioxide, and 1 mole of carbon dioxide is the same as 44.0 grams of carbon dioxide. Moles carbon dioxide cancels, and that'll give us grams carbon dioxide. So 18.4 divided by 16 times 1 divided by 1 times 44 gives me 50.6 grams of carbon dioxide. So that's if by chance methane winds up being the limiting reagent. We don't know yet, because we need to take the 22.7 grams of molecular oxygen and run it through our process of going from grams to moles to moles to grams. So 1 mole of molecular oxygen is the same as 32.0 grams of molecular oxygen. We need our stoichiometric ratio, that 1 mole of carbon dioxide is produced for every 2 moles of molecular oxygen that are consumed. So grams O2 divided by grams O2, moles O2 divided by moles O2, and now 44.0 grams carbon dioxide is the same as 1 mole carbon dioxide. So moles carbon dioxide will cancel, and that would give us grams carbon dioxide. So 22.7 divided by 32 times 1 divided by 2 times 44 would give us 62.4 grams of carbon dioxide. So now we do our comparison. We've done our both reagents. We look at the 2 theoretical yields, and the ones that's the lesser amount, that's going to be our theoretical yield. In that our methane is our limiting reagent, and our oxygen is our reagent in excess. We could add a part B to this problem. What is the percent yield if 42.7 grams of CO2 are recovered? So our percent yield is equal to the actual yield divided by the theoretical yield times 100%, or 42.7 grams of CO2 divided by 50.6 grams of CO2 times 100%, 42.7 divided by 50.6 times 100. Now you give us 84.4% yield. And we can only work this problem if we knew what the actual yield was.